Okay. And as usually, I will share the screen with you. Are you ready, Alejandra? You are okay? During my first lectures, I touched essentially the dominant mode of variability of the ocean and the associated ocean processes that encompass scales from the seasonal cycle up to decadal scales. And today we'll move to something different. We are talking still about variability of the ocean, but in this case, the major our attention will be focused on the spatial scale. Before we classify the processes in terms of time scales, seasonal cycle, interannual variability, decadal variability. So the emphasis was on the time scale, even if the process has a spatial dimension. And you may remember that using the UF analysis, we can split the variability of a system that evolved in time and space in two components, the spatial component and the time component. And all the indexes, all the or large part of the processes that has been discussed under these variability scales are or refer to the dominant or to the dominant modes of variability. So to the splitting space and time. So all this process has a spatial dimension, but the classification and the emphasis has been put on the time scale. In this case, we move from the time scale to the spatial scale. Again, we see there is an associated time scale, but in our case, the important part is the space scale. And talk something about the ocean eddies. It's interesting to see that how the observing capacity has changed the perception of ocean circulation that even the experts had, and until the first satellite launches and the first picture of the Earth from space, the conception or the conceptual model that oceanographer had was essentially related to quite smooth movement of the ocean. You have waves for sure, but all the rest was smooth, slowly moving gyres and fast-moving boundary currents, but sort of linear ocean, moving very slowly. But by then, new instrument detected that ocean circulation also contain vigorous, coherent structures called eddies at special scale from 100 kilometers and smaller. You see here a very nice example of an eddy, ocean eddy, clearly spiraling movement, and probably here you have some biological traces like phytoplankton that shows or track this spiral in the ocean. And here you have I think the West Coast, American West Coast, and you have chlorophyll here, and chlorophyll can be assumed as a tracer of the movement of the ocean. And this front is quite irregular, and you have rings here, or sort of filaments that are dynamically modifying the structure of the coastal boundary current. And why we call coherent structure. This term comes from geophysical fluid dynamics, and if you look at the vorticity, so of the vorticity calculated of the current, eddy current, you can identify that an eddy is characterized by the constant vorticity. You have a polar. We have the polarity of the vorticity is quite a signature of the of the eddy itself. So if the eddy, all the eddy has a circular motion. First of all, it's important to say, and eddy can be cyclonic or anticyclonic, in the sense that it can rotate clockwise or anti-clockwise according to the hemisphere. And when you have a density anomaly, that is one the other dynamical characteristic of eddy. And obviously they change polarity according with the hemisphere. And most relevant feature of the eddies is the fact that they are not directly generated by the external forcing like wind or density gradient. And they have a different scale to the large scale or circulation of the ocean or the atmosphere, but occur because of internal nonlinear ocean dynamics. We'll have some time to discuss more in detail these issues, which are the eddy features. First of all, we are talking about spatial scale, and the eddy horizontal scale goes from 10 to 100 kilometers. This scale is known as a mesoscale, ocean mesoscale, and the typical eddy lifetime goes from months or to years. It depends on where and when the eddies are generated. But what is quite important is the fact that the eddy are not just swirling water parcel around the center of gravity. It is something more, because the interaction with the eddy, with the tracer, with all the water masses, the surrounding water mass, is an active mechanism of transport. And the eddy transport is the order of 30, 40 sverdrup. The one sverdrup is 10 to 6 meter cubic per second, so it's quite an important part. The eddy transport, and we'll see later, is also responsible of important contribution to the heat transport. And to to quantify the eddy transport is that the eddy transport is equivalent to or grossly equivalent to the amount of the ocean moved by wind circulation or to thermoline circulation. As I told you, eddy could be cold eddy or a warm eddy, in the sense that the core of the eddy could be warmer or colder than surrounding water. This is characteristics that is intimately connected to their origin. We see better in the next slide the motivation for that. You cannot have an eddy without this kind of anomaly or temperature or density anomaly, which is characteristics. So we have two different kinds of eddies, one warm, the other cold. The cold trigger on a cyclonic vorticity, and the opposite for the rest. Why? Because this density gradient triggers the Coriolis force, and the Coriolis force divert the circulation in a circular motion at the equilibrium. And this is also a feature to keep in mind, especially to look at when we look at the effect of the eddies on some biological processes. And again, the mesoscale is important in the ocean, and especially at surface, we can detect all this swirling pattern moving in the ocean, and has the same role, mesoscale, or plays the same role in the ocean as the weather system in atmosphere. The scales are different. The weather system are larger and faster compared to the mesoscale, but conceptually, the role is more or less the same. We go back that you may remember, have already looked at. Now we are interested in look at this part of the spectrum. This is a power density, a spectral density calculated on the current meter deployed in the middle Atlantic region in the open ocean. And we see here that we have a continuous decrease in energy connected to the geostrophic eddy, in which the density gradient is fully compensated by the Coriolis force. And we have large-scale inputs. We told that the atmosphere has a larger scale than the ocean. The forcing field are large. Then we have a decrease of scale toward nonlinear processes, and at the end, you know, the final fate of all the kinetic energy is the thermal energy, the dissipation that takes place at much higher frequencies. The important issue is here that the energy connected to the geostrophic eddy is quite important, especially to certain scale, while as you see here, you have sort of a plateau where the general circulation energy is the dominant part. But in a certain band, the mesoscale band, geostrophic eddies plays a major role in explaining the variability of the ocean. So far, so good. How we classify. We are only talking about scales. The eddy are quite, we have a variety of processes that are shapes like eddies or vortices or similar complex of systems. And one very popular scale to define, which is the spatial scale of a geostrophic eddy, is the Rossby radius of deformation. Why we talk about geostrophic radius? Because the eddies has a life. They are generating, they grow, they move, and then at the end they dissipate. When they are, let's say, mature, they have already reached the balance between the pressure gradient and the Coriolis force. And in this case, the scale that or the spatial scale is determined by the Rossby radius of deformation. At this scale, the rotation effects are as important as the buoyancy effect. We are talking about of the balancing of Coriolis force and the pressure gradient. To have an idea of that, we can establish this or define this radius, which is obtained by the Brunt-Weisler frequency. You can recognize this term as a Brunt-Weisler frequency is the ratio between the gravitational acceleration and a reference density multiplied by the vertical density gradient. The Brunt-Weisler frequency is multiplied by h, which is the depth of thermocline, divided by pi and the Coriolis term. So it is quite obvious that if you have a strong Brunt-Weisler frequency, the Rossby radius will be large, while Coriolis plays a major role. So F is important. At equator, for example, the Rossby radius are not defined. And you can see here also H play a role, and the thermocline depth change seasonally, but change also especially. And that's why we don't have a constant respiration depending only by F, but is the composition, the stratification, the first term, the Coriolis and the thermocline depth. The three elements determine the RI value. Looking at this image, you see that the range is between 10 to 200 kilometers, and we have very prominent zonal structure. And the highest at the equator or at the in off equator tropical area, and minimum at the surface. And near the equator, the Rossby radius is larger than 200 kilometers. What is interesting is that is not only our scales goes this way, but also the size of the ocean respects this Rossby radius variability. In the low latitude near the equator, eddies are much larger than the high latitude, and we see some images clearly show this. And over mid latitude, also the internal Rossby of deformation radius increases westward, reflecting the deepening of the zonal deepening of thermocline. So we can see here quite easily in this area. This area it can be seen also in a so small this small image. We are. It seems that it's quite not intuitive. I understand how the system works in the sense that we have large scale inputs. We have slow and quiet, apparently quite large-scale motion connected to general thermalization, thermal and circulation, or wind-driven, large-scale wind-driven circulation. Always the ocean is a low-pass filter compared to atmosphere, also the daily cycle of heat flux, for example, and as a sort of natural smoother the ocean response. Instead, ocean itself is able to create structures which are faster, quicker, and full of vorticity. Vorticity is always difficult to generate, as in the ocean interior, vorticity is assumed to be conservative tracer. Potential vorticity, which is related to relative vorticity, is a very important and quantity that is for sure dominate all the quasi-dystrophic dynamic of the ocean. So, and which is the mechanism that generate this, the origin of the eddy, kinetic eddy. And we start to look at this, the upper part of the figure. And we have 2 layers fluid, one characterized with a density rho A, the other one characterized on the density rho B. And we assume to have 2 water parcels, same dimension, but different density, one belonging to the upper layer, the other one to the lower. There is some potential energy associated to this state, and assume to change the 2 water parcel, moving the denser part upward and the lower part downward. In this case, we have an increase of potential energy, and the system is unstable. You have denser water in the upper layer and lighter water in the denser layer. So whenever the shifting or displacing mechanism stops, there are some potential energy which is ready to be released. But in this case, when you have a vertical exchange, you have just a rapid movement that move the one parcel in the other, and instead of the other. So no lateral velocity is created, just vertical movement, and probably some mixing due to the shear connected to that at the end will cancel the presence of the two water parcels there. So vertical exchange cannot explain that, but has some important mechanisms that is retained. Instead, to have a vertical exchange, as in the upper part of the figure, we can examine the slantwise exchange. Imagine that instead to have a two-layer fluid separated by the horizontal interface, we have the isopycnals are slanted this way. Here we have Z, so the density. Here we have Y, so meridional section of an idealized ocean, and we have the density that goes upward with the latitude, and the full line represents this sloping isopycnal. Imagine you have again our water parcel belonging to the low density, high potential temperature here, and we have a high density, low potential temperature here at this isopycnal. These are denser than that one, obviously. And the move of A to B is along the path identified by L. This path is not horizontal, has a certain angle. When you move the water parcel there, you have created an increase of potential energy. And this potential energy is due to the fact that if we have a lighter water parcel at the high density isopycnal and vice versa, we have a low density water parcel, a high density water parcel in a low density isopycnal. When the disturbance ceases, the two water parcels can go back, and when they go back, they transfer potential energy in kinetic energy. And since this happened on a spatial dimension, and displacement is large, and also in X, not only in Z. In Z, the displacement could be a limited amount of meters of zone, and not the vertical scale of the ocean is much lower than the spatial one, but the movement or the time that it takes place of in the lateral displacement, and is enough to make Coriolis force to work and to divert the pathway of the two particles, water particles, going back to their equilibrium area, and this creates the circulation of that generate the eddies. And you see here that we have generally one positive and the other negative verticity eddies, and this mechanism, idealized mechanism, creates always a couple of different polarity eddies at the same time. Angle alpha plays a role in sense that the potential, the optimal release, the maximum of the potential energy release occurs for a change at angle L alpha, which is half the slope of the isopic net. This can be analytically demonstrated. And obviously, in general, you don't have perfectly parallel isopic, the density, the movement of the water parcel are not adiabatic and so on. So there are a lot of idealization in this process. But what is important is to have a slantwise orientation of the isopic and external movement that trigger this displacement. We don't discuss this. There are some mechanisms. One is the baroclinic instability, which is quite a complex issues that is not part of this course, I think, and it takes place when you have a strong vertical shear of the horizontal velocity when the horizontal velocity accelerates, for example, in the surface layer, and in the lower layer you have a quiescent ocean. This increase of vertical shear horizontal velocity can provoke instabilities that can lead or can trigger this kind of displacement of water masses from one isopic to other against the pressure gradient. Do some work, create potential energy that is released, and this potential energy release is eddy kinetic energy. This is more or less, not into detail, not perfect, I do agree, but as the major concept, this explains why the eddies has a warm or cold core compared to the surrounding water. Without this displacement, without these anomalies, density anomalies, no traditional or geostrophic eddy is possible. And this another way to look at this is the fact that when you have a pulse of or box-like anomaly in density in a two-layer fluid, as we have here, dashed line, is more or less what happened when you have a displacement of water parcel from one equilibrium state where the water parcel is lighter or is denser and is moved in a lighter fluid or in a lighter toward a lighter isopic. Then you have this kind of anomaly. You have an initial state where a density anomaly, box-like density anomaly, characterized by an anomaly density, positive anomaly density delta rho. This density anomaly is surrounded by the lighter fluid layer characterized by the rho density. So if you leave this evolve without any other forcing here, and in a non-rotational framework, the final state, as expected, is a homogeneous final state where the density, every density, is equal for all of them. and as the weighted average between the density of the first layer and the density of the second layer included the density anomaly. What happens if you add the rotation? If you are in a rotational framework, again, you have the X and Z shape, you have this box-like anomaly, and then with a density gradient with the surrounding water. At the end, we have a non-homogeneous distribution. Why? Because this lateral spreading, which is in 1D, which is the only way to mix or distribute the density anomaly. Here you don't have any pressure, any forcing to limit the, or to reduce the pressure gradient. Here you have it. You have the Coriolis term that acts, and the spreading is limited due to rotation to a horizontal scale, which is governed by or Rossby radius of deformation. And this limited spreading leads to the horizontal circulation around the perturbation. So the 1D problem is no longer 1D because of the term of Coriolis term. And if you remember the momentum equation of the Navier-Stokes equation set, you have, in case of no Coriolis term, the two component, the X component or the Y component of the momentum equation are independent. They have no connection. And you can solve them independently, X, Y. When you have the rotation, then you have a Coriolis term, and in one case, in X, you have a dependence of Y. And the Coriolis term also in the V term, so in the Y the direction, has a dependency on the component of the component along X. So rotation automatically implies a two-dimensional, at least a two-dimensional motion. Even if we have a 1D perturbation, final state has also a two-dimensional solution, not a single one. This is also important as part something to do to the what we saw before. We have a slantwise exchange, and the rotation plays a role to in the restoring of the system, and this rotation prevents the full restoring of the condition, while transforming the energy or the potential energy in eddy kinetic energy. And the scale in which this happens is a special scale, is again the Rossby radius of deformation. And we're talking about space scale, but we can talk about time scale. And we can use the characteristic growth rate for eddies, and which is given by the ratio between the space scale and the velocity scale. The space scale is easy to it's not difficult to have a space scale, since we talked up to now the Rossby radius deformation. So we assume the Rossby radius deformation as the special scale. And we can calculate the characteristic velocity scale for eddies by making some simple calculation. It is not here. You can find in the Williams Follow textbook that I suggest you to look at in case you want to have the curiosity to see how some solutions are obtained. And they propose a simple calculation to calculate the characteristic velocity scale for an eddy by looking at the efficiency of the conversion of the potential energy gained in the water pulse in the slantwise exchange into kinetic energy. And this energy is the order of the proportional to the of the depth of the thermocline and to the velocity, or the shear velocity of the U component. This term is obtained as the term due to the thermal wind. You may remember the thermal wind says that the modulus of the shear, the horizontal or the zonal shear velocity is given by the ratio between the g, which is the acceleration, gravitational acceleration, divided by the reference density rho and f, multiplied by the horizontal density gradient, or the zonal density gradient. And the zonal density gradient is proportional to the zonal shear. So having an idea of the density, horizontal density gradient, you have an estimate of the zonal shear and also modulated by the edge. So we have a scale calculated this way of the velocity of the eddy, and combining the two, we obtain a typical growth time scale, which is due to essentially is the ratio between the Brun-Weisler frequency divided by f, and this ratio is divided again by the u, the vertical shear of the zonal velocity. This is quite a back of envelope calculation, but it's a very good agreement with the eddy, or the growth period calculated by the eddy theory, which is the fast growing mode of linear baroclinic instability. And so this, just to say that this, simple estimates is not far from what is obtained what more sophisticated calculation, taking into account the whole, simplified baroclinic instability theory provided by eddy. Just to, the difference is in the factor 2, and here we have a different coefficient. I remember 0.31 or something like that. So it's not far from that. If we have some, well, realistic number for mid-latitude. You have the Coriolis term is 10 to the -4 second -1. The stratification as given by the Brunweiser frequency is 3 multiplied to -3 second -1, which is quite well stratified ocean at mid-latitude, and the shear is 0.1 meter per second over 200 meter, which is a vertical shear of on average depth of the ocean. And the eddy here is order of 10 days. And in practice, you have some example of a growing eddy train growing along the Algerian coast. There's the Algerian current that is formed in the North Africa side of the Mediterranean, and we have a current formed by modified Atlantic water rimming this current coast going eastward as the large-scale general circulation of Mediterranean imposes, and there are instability here formed probably by baroclinic instability that creates vortices as a continuous transfer between the kinetic energy to potential energy, to potential energy to eddy kinetic energy that form this eddy that grows in time, and then at the end they dissipate. The growth rate is the order of week, is not constant, but is not far from those foreseen by this simplified back of envelope calculation of the time scale of the eddy. It's important to note, this is the growth of a train of different eddy, but looking at the simple, in different image, a single eddy, you see the Algerian eddy, AA, here, and after look at this as a mark, and you see how the eddy is growing, but also propagating westward. So we have two components here. One is the general circulation, the Algerian current, the moving eastward, and then you have anticyclonic eddy that is moving this way, and the net velocity is the composition of the two. One recirculating, the other one is the general movement of the water column that is connected to general circulation, that impart a net west-eastward movement, even if the velocity here is a composition of two. So the eddy are circulating around their center of mass, but they are also embedded in large scale circulation that move them along the general trend. So eddy are not steady generally, but they are also moving according, or they are influenced of the general circulation too. There are other kind of eddy which are not surface, and that's a quite interesting one, and they've been discovered relatively recently, and we have the Gibraltar Strait here. Gibraltar Strait is this narrow strait that connects Mediterranean to the North Atlantic. And we know that the outflowing Mediterranean water is saltier, and this salt also influences on the long run all the intermediate water of North Atlantic, and possibly there's a lot of discussion on that in the past, can influence the densification of the water masses of the North Atlantic up to influence the dense water formation of in the Labrador Sea. So influencing the whole AMOC and possibly modulating them. And this is not fully understood, but or agreed. The Atlantic Mediterranean community is sustaining the important role of the Mediterranean and the need to include in the global model also the Mediterranean component. And others say, well, the fact is there, but it's not so important, and the salinity is largely due to the tropical dynamics of the Atlantic itself, and not as this variability cannot be ascribed to Mediterranean. I don't have a clear opinion on that, but for sure, what we there was some interest in tracking the output of the Mediterranean, and what has been discovered. You do that here, then the water. Mediterranean water intermediate layer, not its surface, because the circulation at the Gibraltar Strait is a 2-layer, and here you have at surface the Atlantic water is lighter, goes into Mediterranean, while a counter current is below the Atlantic water entering the Mediterranean that goes outside, and is denser and saltier. And you see here more or less the same area here. How is the salinity jump from 35.5 to 36.7, so more than one difference. The difference of more than one practical salinity unit between the two water masses, which is a sensible one. It's not, let's say, a constant stream, but instead is mediated by a large number of swirling movements that are associated at the eddies, or Mediterranean eddies called medis, which are characterized by anomalies in salinity instead of, or not only in temperature, but also in salinities. And this profiles has been obtained by release almost simultaneously a number of buoys that are freely go with here you see better the experimental setup has been almost immediately released in order to create, to detect this evolution. So eddies are important also in depth, not only in surface. They have important role in mediating the exchanges between Atlantic and Mediterranean and Atlantic, and transporting the active properties of the Mediterranean water into the Atlantic interior. But the eddies are important not only in this case, but are ubiquitous. And as I told you, the onset of the atmospheric and the satellite oceanography shed light on the actual importance of the eddy. And there was a sensor put on board a satellite-borne sensors for that measure the surface height anomaly of the sea. And it's been topic Poseidon, then Earth, then JASM. There are a lot of series of satellites that host such active sensors. They are sort of a microwave radar that launch signal, and from the reflected wave, they are able to detect or calculate the sea surface height anomaly. Anomaly means that you calculate an average value, and you don't need to know exactly which is the mean level, which is always an issue and is difficult to do. But you just look at the difference between the reference state. Well, you can have an anomaly, and this anomaly, you see, can be related to the presence of a small scale feature, which are very well effective or present here in correspondence of the western boundaries current. They're more effective in doing that. This is Kuroshio current with the western boundary current of Pacific. It is the Gulf Stream. Then we have the Benguela current, and then the Atlantic circumpolar current, which is quite an dynamic area that spinning around the whole southern Ocean. Then you have some well-known feature like El Nino here. There are El Nino tongue, but here, for the moment, we forget it. We are just interesting in looking at the scale. You know that the scale of the ocean of this pattern tend to reduce with the latitude as we expect from the theory or the analysis of the behavior of the rock deformation radio, and are larger on the western coast, where the deepening of the thermoclimatic spectra as the theory predicts. And the message is the ocean is an eddy ocean, essentially. And when you look at a single image or a single observation, the presence of an eddy can substantially perturb the measurement of the observation you do, unless you have a satellite or a large-scale picture that can put in the proper context this observation. So a single observation is good to represent well what happened in a single place. It's difficult from single observation only to reconstruct a large area, especially if you want to have not a synoptic view, but a general large-scale long-lasting image of what is the ocean in a special part of in a geographical area. While because the eddies are there, are moving, are active, it changes with the scale of, as we saw, of weeks, and so you do need either a lot of observation, or you have to have a satellite, and better you have to combine in situ observation that are vertically resolving satellite that gives the picture of what's happening surface or in a near surface layer, and then integrate in the model that are optimal interpolator to give the analysis, which is the best we can do in order to have a picture of what are the water mass, what are the circulation with the surface height in a certain area in a certain moment. Just to reinforce that the eddy are forgotten by a large scale of the time scale we are look at in the past. The long-term variability don't care about this fast-growing anomalies or perturbation, but whenever you look at the ocean in one picture like this one, you see how much of the total signal can be ascribed to the small transient coherent structure like the ocean eddy. And this is something which is of utmost important to keep in mind, because whenever you have, or if you have a chance to make observation or do modeling, eddy will be always a pain in the neck, because they can perturb substantially what is the average state, which is often what we want to achieve. Eddy move, eddy can trap core of water masses. They affect the property of the water masses in this sense. So I would to start to move from the perspective of ocean dynamics to the perspective of the ocean properties. And oceanographer talk often about ocean tracers, that are properties of water masses that are used to deduce small scale flow patterns or large scale ocean circulation, water mass formation changes, dating of the water massing, and carbon dioxide storage and uptake. This is quite an important issue, and we'll talk about later on Friday. And on that, this is an operational definition in the sense that we don't care of the chemistry, we don't care of biology, we don't care about other properties. We just use this these ocean properties as support for the definition of which is the ocean circulation, which are the typical scales, which are the pathways, and so on. And so in some sense, we exploit the presence of these ocean properties for physical for physical exploitation. And this is why that the name gain so much popularity. But we have to acknowledge that the tracer are much more than that, because a tracer can be active. An active tracer is called active when has a direct influence on ocean dynamics. For example, temperature and salinity equation are integral part of the Fourier-Navier-Stokes. Temperature is a thermodynamic, represents the thermodynamic of the ocean, and the density equation includes pressure, but also temperature and salinity. So we cannot have a realistic description of the ocean without TNS. TNS are the typical active tracers that are considered in the ocean. But also, the TNS are the most simplest way to characterize the water masses. And TS diagrams are commonly used to define the water mass characterization of certain areas. There are also other kind of tracers that can be defined as passive, like dissolved oxygen is everywhere in the ocean. And but the dissolved oxygen is not included in the dynamical equation governing the ocean. So it's under this aspect as passive. You can have a conservative tracer like the chlorofluorocarbons that remain constant following the fluid parcel. They don't have an internal decay or increase or transformation ratio. And CFCs has been released in the atmosphere since 1930, and they are known, they're used as coolant or refrigerant or propeller in aerosols and so on. And it turned out that these CFCs are very effective greenhouse gases, as has been banned. So we know perfectly the onset, the increase curve, and the reduction curve in the atmosphere. And this is a sort of a timer that can be exploited to see the age of the water mass in the interior. And the CFC concentration, because it's conservative, can act as a perfect timer and triggering, which is the last time in which this water mass was in contact with the atmosphere, since the atmosphere has well-known curve of concentration curve of CFC, and then we can calibrate this timer and giving an age of the age is the formation of the time of formation, or the time passed after the formation of this water mass. Last time that this water mass was in contact with the atmosphere, and when its TNS characteristic was set by the formation process. We have another kind of tracer, which is reactive, and when it grows or decay with time. CFCs are there and cannot get rid of it, while radioactive isotope like cesium 137 is a reactive, or is can react also with the biology, but also is tend to decay with time, and because of the radioactive degradation of this isotope, and the half-life time of this isotope is about 30 years. And the Chernobyl event, where a lot of radioactive nuclides are being delivered in the atmosphere, this was a substantial input in the water column. We have a natural fertilization event that had given oceanographer the opportunity to calculate quite well the time age, the age of water masses using this kind of radioactive isotope. Another important reactive tracer is the CO2 compounds in seawater. You know, CO2 is dissolved in seawater, but also is hydrolyzed in terms of bicarbonate or carbonate. So the inorganic carbon system as a quite an important trace in the ocean, but is reactive, is not constant, is changing according with different condition, pH, and so on. So is there, is conservative, but since is reactive, tends to grow or decay according with time. So we can have passive and reactive tracer, dissolved oxygen and calcium and CO2 inorganic carbon cycle are two examples of passive reactive tracer. All of them share a unique property. They move with the water parcel they are in. So they don't have to the first glance, they don't have at large scale of individual motion. They are passively moved by the water masses circulation. So, and this is why they are tracer. If a tracer has an independent move or dynamics, well, it's difficult to use it as a tracer because the tracer are tracer since they trace the water mass movement. Again, we go back to the role of the eddy or the role of the dynamics into the spreading tracers. Tracer track the movement. What are the movements of the ocean that can affect tracers? And obviously, eddy are, we saw until few slides before, the importance of the eddy in steering a tracer, and has an important impact also in physical and biological system, because if you move TNS, you change the density. If you move nutrients, you can trigger primary production. When you have advection, advection means that you have this larger scale picture, and general circulation is essentially an advective process that translates fluid and any accompanying particles or tracer by this background flow. You see here the Gulf Stream. The Gulf Stream is part of general circulation, and it moves smoothly this temperature northward. Then here you have eddies, and this is part of the Gulf Stream, just changes scale. And here the dominant scale are as mesoscale. Here you have a ring, and here you have a fluid that creates the two eddies. As we saw here, you have a positive, negative, positive, bipolar, dipoles created by the instability of the currents, and that gives way to the mesoscale eddy. And you have another process connected to eddies. When you have the interaction between two water masses, the eddy tend to, because of their rotational motion, tend to draw patches of tracer in narrow filament inside. You don't have homogeneous first step of homogenization into the eddies. You have a process that's called steering that draw patches. You have filaments here of the connected to the coast current you saw this earlier, and is no or limited diffusion here. The properties of the water column are still there, they are mixed, and you may remember the Taylor-Pullman theorem. You've already seen that, and it told that in geostrophical adjustment you have vertical homogeneity of structure. You have Taylor curtain that is homogeneous in vertical, and this happened also in the ocean. The tendency is to maintain, especially in geostrophic, the vertical coherence, and this means that also the property are also homogenized in vertical, and you can have sort of a 2D and realistically 2D structure that is in place. So when the water masses that generate, or the pressure gradient due to the different water masses involved in the eddies, the tendency is to create filaments, instabilities, and filaments that create the steering process. The steering process is a prerequisite to go further in the spreading process, going to a lower scale, or a different scale. We have the so-called the eddy diffusion. We'll talk about in the future, I hope so. Which is the systematic transfer of tracer from high to low concentration due to the fine scale non-negligible correlation with velocity and tracer fluctuation. You remember, you have the Reynolds average equation. You have the component, the fluctuation component, which is the velocity can be split in a mean velocity and a fluctuation. The same can be done for any tracers, temperature salinity, for example, and you can have the nonlinear term, advection term that is responsible for the coupling of the two statistical components for U and the tracer. And this statistical correlation is not always zero, could be different to zero. And in this case, this correlation, non-negligible correlation in velocity and tracer, is the responsible for the diffusion. Eddy diffusion is the parameterization of large scale, or can be parameterized, used to parameterize to large scale these eddy turbulent, eddy-driven turbulent flow that is responsible for the mixing. And the eddies are example of Korean structure. They are the primary responsible for the eddy diffusion. If you don't have eddy, this correlation term tends to be negligible. So that's why eddy diffusion is called eddy diffusion. But at the end, if you are steering, you have eddy diffusion. This is the larger scale that process, or relatively large scale, but at the lower scale is the true mechanism that at the end is mixed the fluids, is the molecular mixing, which is the irreversible transfer of fluid across a tracer gradient, which is achieved by molecular diffusion. It's the Brownian motion. And in that case, you can have different kinds of mixing. For example, molecular mixing for temperature is different if compared with the salinity, and as intrinsically different. In one case, the temperature is average kinetic energy of the tracer of the even seawater. And salinity, for example, is the composition of different ions that obviously can move in the ocean or in the surrounding water molecules in different way. The first, sorry, I have to correct myself. The first temperature is the average kinetic energy of the water molecules. Instead, salinity is the Brownian motion of the ions that compose the salinity. So there are two different quantity involved in that. Obviously, we have different rates, but essentially is the agitation of the molecules that is responsible for this mixing, which is active a very small scale. We can speed up a bit here because it's something that you surely have already seen. The evolution of the generic tracer in 1D in a pipe, so as the opposite of the derivative of the flux F. Flux is we've seen there are different kinds of fluxes, but you have a flux incoming and a flux outgoing in a pipe. In the center you have a water parcel, and the water parcel is characterized by a density, and we suppose that the generic tracer has a concentration of C. The evolution of this is connected to is proportional to the flux minus F, or the derivative, the special derivative F minus with a different sign. And intuitively, you can have the water pass, you have the tube, a pipe, you have incoming flux and outgoing flux. If the outgoing and the difference between the two gives the concentration. If the outgoing flux is higher than the ingoing, the density, the concentration of the unit volume here, unit mass here, is or unit volume, sorry, is reduced because you have more output than input. Vice versa, the rest. You can have different kind of flux. This is the advective flux, as the concentration per unit volume is given by these two terms multiplied by U, and in putting this definition into the previous formula, you obtain this term. If you change rho density multiplied by the concentration of unit mass, we have C, which is concentration for unit volume, simpler. And this is the advective flux, or is time change, time rate of change of the concentration due to the advective process. Then we have the other opposite process. We have molecular diffusion. This is the diffusive flux, which is governed by the Fick's law. So the flux is minus K, which is the molecular diffusivity, multiplied by the gradient along X of the concentration by unit volume of the generic tracer. Then, if you put it in the equation, we have the diffusion equation. So we have the first equation we saw before. Number one is the advection equation obtained by this generic trajectory budget, then we have just input, in this case, the advective class into the generic budget, generic tracer budget. Then you have the same kind of equation, which is turn out to be the diffusion equation, just putting the fixed law into the generic tracer budget. Combining the two, we obtain what's called the Burger equation, or the advection diffusion equation. You can recognize that the time rate of change of the concentration of the generic tracer is obtained by one term, which is the view due to the advection. The other one is due to the molecular diffusion. And what it turns out to be quite natural to see what the two scales are dominant. If we substitute the first term, which is typical length scale, velocity scale, and concentration scale, and the same for the diffusion term. K is known, it's very small, 10 to the minus 6 meters square second minus 1. Then you have the concentration, and then you have the spatial scale. If you make the ratio to, you obtain the Peclet number that gives an idea on how much advection is, which is the two is dominant. If Peclet is less than 1, means that you have a diffusive process, dominant process, or better, a molecular diffusivity process, dominant. In the other case is advection will be dominant. And in most of the oceanographic situation, when you are far from the very narrow boundary layer, bottom boundary layer, for example, advection is quite large, is dominant one, because U is order of meter, L is large, could be kilometers or 10 kilometers, for example, for an eddy. And in an eddy, you can have advection, which is much, much more important for the in the equation, while the molecular diffusion is is almost negligible. So sometimes we are not far from reality when we move, when we assume that the fluid is inviscid, we don't have any diffusion, and the geostrophic balance, the thermal wind equation, and others idealized solution don't consider diffusion diffusive term as in the equation, and still they have some explanatory potential. I think I have to stop here, and as usually, I will give you the slide, and I will send an updated version also of the notes at the end of the next lecture. Will be the last one on Friday, and I, as usually, I'm available for question and clarification on. Please feel free to send me an email on that if you have issues, and if you don't have a question, stop here and have a good day, and see you in the day after tomorrow. Ciao, bye bye, and see you soon. Ciao.
Bye.
Thank you.
Ciao.
Ciao.
Thank you.
Thank you. Bye.